Hello, my name is Devdeep Ray, and today I'll be presenting Prism, handling packet loss for ultra-low latency video. So we're going to be talking about how to handle packet loss for ultra-low latency applications like cloud gaming. First, in traditional gaming, the inputs are sent over USB or Bluetooth to a local device where the rendering happens and all the heavy computation happens, and then the rendered content is sent to a monitor over HDMI or DisplayPort. On the other hand, on cloud gaming, the user inputs are sent over the internet to servers in a data center where the rendering and computation takes place. The rendered content is compressed as video and streamed back to the end user where it's shown on a low power device. It needs to achieve parity to local rendering, and therefore it must have very low end-to-end video frame delay, and it must have very high video quality. Now, the internet is a best effort service, and which means packets can be lost while streaming, and packet loss is very harmful for streaming video. This is because video compression algorithms use reference-based encoding and have inherent state, which means if you try to decode frames after a packet loss, it'll result in visual artifacts. So for example, on the right here, we have a frame that was decoded with some loss, and it has a lot of jarring artifacts which are not acceptable for applications like cloud gaming. There are various factors that affect how an application performs under packet loss. First is how much bandwidth is available and how is the bandwidth being used. So for example, a particular video compression scheme can have a different effect on video quality and loss resilience. The loss recovery technique also affects the performance of the application under packet loss. For example, specific loss recovery techniques may have different impact on the frame delay and different impact on the video quality. The delay variations and jitter that can be seen on the internet also affects packet loss performance. This is primarily because it affects how packet loss is detected and how quickly you can detect packet loss when it occurs. So how do we mitigate packet loss? There are two broad categories. The first is proactive loss mitigation. In proactive loss mitigation, techniques like FEC can be used, which is forward error correction, where you transmit redundant data in order to recover from lost packets. The key benefit is that this process does not involve the sender when a packet loss occurs. The receiver can on its own figure out what the original data was, which means it avoids a round trip penalty in order to recover from the data loss. The downside is that low latency FEC schemes are generally not resilient to bursty losses, which is common on the internet, and loss recovery is not guaranteed if many packets are lost, which means you still need reactive loss recovery. And that's going to be the focus of this talk here. Now, classical reactive packet loss recovery schemes for video can be classified into two categories. The first is retransmissions. In this case, lost packets are essentially retransmitted by the sender. This process incurs a one round trip delay in order to detect the loss and retransmit the packets. And there are additional delays because while the packets are being retransmitted, the decoder cannot decode any of the subsequent frames. And so these frames get blocked at the decoder until all of the packets have been retransmitted. The second approach for recovering from packet loss is decoder state reset using an iframe or an IDR frame to be specific. The benefit of this approach is that the frame delay is very low because once it receives an IDR frame, it does not need to catch up to the pending frames and can simply discard that data and display the latest frame. But even this approach incurs a one round trip delay because of loss detection. And the other downside of this approach is that iframes significantly affect the video quality. So iframes do not leverage temporal redundancy. They only leverage spatial redundancy, which means they have low compression efficiency. You can see that in this graph, where for a particular bitrate, the quality achieved by iframes is much lower than the video quality achieved by pframes. And conversely, for a particular video quality, you require many more bits to encode the data at the same quality as iframe compared to encoding the video frame as a pframe. The second issue is that the video quality of a pframe stream also depends on the video quality of past frames. This means that if you have a single low quality frame, it affects the video quality of a number of subsequent frames in the future. For example, over here, the orange line depicts a video encoded as a pframe stream, which is a steady state pframe video quality. And the blue line is again pframes, but with periodic iframes inserted, which are at lower quality. As you can see, when the iframe is inserted, the video quality drops instantaneously, and it takes a long time to recover back to the steady state. So now that we have some high-level background on video compression, let's talk about the design of Prism. So consider a scenario in which we are using iframes for recovery. So originally you have a p-frame stream, the video quality is high, and the steady state p-frame video quality. Now a packet loss occurs, and the next few frames are sent as iframes. The quality of these iframes are going to be much lower. Once loss recovery is complete, it recovers back to using p-frames, and the video quality gradually kind of stabilizes back to the original p-frame video quality. Now, the problem with this approach is that you have this drop in quality as well as a drop in quality after loss recovery, which sustains for a while. The second issue is that if you wanted to reduce the one round trip penalty by using techniques like loss prediction, if you have a false loss prediction, you will still incur this video quality penalty, which means that iframe-based recovery is not compatible with loss prediction. So the key observations that Prism makes are, first, p-frames are much more efficient than iframes at compressing video. This is because they leverage temporal redundancy. Second, video quality has diminishing returns with increasing bitrate. And third, the video quality of a p-frame not only depends on the bitrate of that frame, but it also depends on the video quality of the past frames. So this slide, we have a high-level description of Prism's core design. So originally, you again have your p-frame stream where the video quality is high and at steady state video quality. Once you have a packet loss, Prism transmits two separate video streams. It continues the original p-frame stream at a very low bitrate, and it uses the additional available bandwidth to transmit a secondary iframe stream. So what's the benefit of this approach? So now at the receiver, you have these two video streams during loss. You have the lower quality iframe stream, which is also low latency. And you have the secondary p-frame stream, which can have a higher delay during loss because some of the older packets are still being retransmitted. Now, if you look at the video quality, when real loss occurs, you get a drop in video quality, and this video quality is slightly lower than what you would get with just iframes. But the benefit is once loss recovery is complete, the quality quickly jumps back up to the steady state p-frame video quality. So one benefit comes from this part of the SSIM curve. The second benefit of this approach is that if you were to use very aggressive loss prediction techniques where you have a lot of false positives, in the case of a false positive, the decoder can simply continue decoding the video with the p-frame stream, which over here is the pink line during loss, and that has much higher quality. And thus, Prism's design also helps with loss prediction. So now the key question here is, how do we split this bandwidth in order to optimize the video quality? The optimal split depends on many factors. The first is the available bandwidth. The second is the relationship between bitrate and SSIM. The third is the SSIM dynamics of p-frames. The fourth is how long the loss lasted. And the fifth is what is the rate of false positives for the loss prediction mechanism being used. Now, one problem with this is that the bitrate SSIM relationship and the SSIM dynamics of p-frames are not known in real time. You need to wait for the frame to be generated, and you don't know what the future frames are going to behave like in real time. And to solve this problem, Prism uses an offline scene optimization and SSIM modeling technique, which speeds up this offline scene optimization process. So essentially what we do is we calculate bitrate allocation for specific video scene types, with the hope that it generalizes across that particular scene type. The second problem is that the duration of loss is not known in real time. You don't know how long the loss is going to last in the future, and this is important because we need to care about how the p-frame video quality converges after loss recovery is over. So in order to handle this, Prism's optimization uses an optimistic assumption where essentially the allocation for each frame assumes it's the last frame in loss recovery. And this is also used in real time. And if the loss event is not over by that point, we fix all of the allocations for the previous frame and calculate the optimal for the next frame. So this is basically a greedy optimization assumption. Now I'll present some brief results from our paper. So over here, we have a time series with random packet loss. On the left, we have iframe-based recovery, and on the right, we have Prism. In the case of iframe-based recovery, when losses occur, the video quality drops significantly, And once loss recovery is complete, the video quality slowly recovers to the steady state video quality. The benefit of iframe is that you have very low delay, as you can see over here, because the decoder never needs to catch up to pending frames. On the right, we have Prism. So in the case of Prism, when loss occurs, the video quality is slightly lower than what you would get with just iframes during the loss event. But soon after, when loss recovery is complete, the video quality quickly jumps back up to the steady state video quality, as you can see over here. So that means that Prism achieves high video quality. And in terms of delay, since it just decodes the iframes during loss, it still achieves very low frame delay. And so it has the low delay benefits without the quality penalty of iframes. Compared to packet retransmissions, which is shown on the right over here, when a packet loss occurs, there's a very large delay spike, which takes a long time to recover. And this is unacceptable for very low latency applications like cloud gaming and cloud AR and VR. So Prism achieves much lower frame delay compared to retransmissions. In the paper, we have a lot of additional evaluation. We run simulated gains across different bandwidth regimes and loss durations. We demonstrate that per scene optimization is necessary and also sufficient. And we also evaluate the performance of an actual real-time implementation of Prism under random loss and loss caused by cross-traffic. Now recall that Prism works well with loss prediction mechanisms where there's a high rate of false positives. So in order to evaluate this, we implemented a neural network-based loss prediction mechanism. This was trained on packet traces from the MLabs project. So at a high level, what it does is it looks at network statistics from the last 200 milliseconds in order to predict if there will be a loss in the next 50 milliseconds. On the right, we have an example of Prism's loss prediction in action. The blue line over here shows when actual loss occurred, and the orange lines show over here when Prism's neural network predicted that a loss would occur. And as you can see, there are quite a few false positives, but Prism's design enables high video quality in such situations. And combining with loss prediction, this ends up reducing the end-to-end frame delay. This can be seen on this graph where the first bar we have over here is iframes. The second bar we have here is iframes with loss prediction. And as you can see, it has much lower video quality, but it does have lower delay. On the right, we have Prism with loss prediction, which achieves very high video quality and low frame delay with loss prediction. So there are some considerations over here, which is the computational requirements. In Prism, we use an offline scene optimization, which eliminates the need for optimizing in real time. So you don't have to do complex video encoding sequences in order to determine the optimal split. The second is Prism uses SSIM modeling, which actually allows real-time re-optimization if needed very quickly. For example, this could be necessary if your rate of false positives of the loss prediction mechanism changed because the network properties changed. In addition, Prism requires 2 encoders and 2 decoders, but note that it's only required when packet loss occurs. It's not required during normal operation. On the sender side, 2 encoders is not a problem because it's a cloud server with a large GPU, which typically have multiple video encoders. On the decoder side, it also requires 2 decoders when loss occurs, but the observation here is that the decode speed is typically proportional to the bitrate, and since Prism splits the overall available bandwidth across 2 streams, it doesn't actually increase the amount of computation by much. So to summarize, Prism is a packet loss recovery technique for very low end-to-end frame delay and high video quality. And it leverages the high bandwidth regime, which is specific to applications like cloud gaming. It is a holistic approach that optimizes video quality using codec and network level optimizations. Prism's design considers the 3 key aspects of a video streaming system together, which is first, what to transmit. Prism splits the available bandwidth into 2 separate video streams, one which achieves low latency and the other which achieves high quality. Second, Prism splits the bandwidth across these 2 streams by optimizing for video quality based on the video type, the available bandwidth, the loss duration, and the loss prediction accuracy. And third, Prism enables the use of loss prediction, which can speed up loss recovery process by predicting losses and initiating recovery early, which eliminates the 1 round trip penalty. And that concludes my talk. Thank you.